Our panelists, and first of all I have Sarah Carpenter.
Hi, my name is Sarah Carpenter. I'm a technology integration coach for K-5 elementary schools. I've got 3 different schools, and I serve about 150 teachers and about 1,000 students. My passions are assistive technology and computing and robotics.
And next we have Ms. Lisa Rode.
Hi, I'm Lisa Rode. I'm a 6th grade classroom teacher in Springfield, Virginia. I'm also a CS for All Teachers Community Ambassador along with Nancy. Outside of school, I also am a curriculum developer for Dexter Industries. My passions include making and building things, robotics, coding, and I especially love finding ways to incorporate computer science concepts within core curriculum.
And I am your host, Nancy McGowan. I'm an instructional math coach, a CS for All Teachers Ambassador, and a National Board Certified Teacher. So at this time, we're going to kick off our webinar with a brief video clip. And if you are listening through your phone, your audio should be good. We are keeping our fingers crossed on audio through the computer. So here goes.
Hello? There are 2 people stuck on an escalator and we need help. Now, would somebody please do something?
Hey, don't worry about it. I'll fix it in a second.
He said he can fix it. All right. All right. That's more like it. He says he can fix it.
So in this video, 2 people are on an escalator. It stops and they are stuck. Their limited experience doesn't prepare them to do anything else. Then a maintenance worker is preparing to ride to their rescue, but then he also gets stuck. So the takeaway here is while most of us have seen this video and we laugh, I love it, because the solution for us seems so evident, yet the individuals are hopelessly stuck. Now we can obviously parallel this to our kids because sometimes they also get stuck and they don't have the tools or the experience to find a resolution. So this brings us to tonight's webinar, which is computational thinking. The phrase CT for educators, it seems like the latest buzzword in education, and Sarah has something that she received in the mail just today on computational thinking. It makes us feel silly, though, as educators to say, I have no idea what CT means, and then also, I don't know how it would even fit in what I teach. Or you may say, oh, I think it's only related to digital devices. Well, everyone's situation is different with devices, but sometimes we have to implement work on a device and it seems like just one more item to our already full plates. So let's try to wrap our heads around how we might define computational thinking. Computational thinking involves solving problems. We're organizing and analyzing data. We're representing through models. We're making a series of ordered steps, an algorithm. We're trying to figure out solutions, but we want to be efficient and effective, and we're also generalizing. I don't know about you, but when I read this, I think of the way that this meshes with math. And then Sarah is thinking how, oh, computer science. And then Lisa's zeroing in on English language arts. So whenever you incorporate new practices into your classroom, there's a certain level of expectations. The benefits of computational thinking simply reiterate and support instructional goals we have for our students. At this time, if you will look at the top of your screen and locate the student icon at the very top up there, we're going to get some audience feedback. So here we go. Your question is, what methods of decomposing numbers do you use? Would it be, and you can check as many as you wish, break apart into 2 add-ins, break apart into more than 2, break apart by place value, or an other. If you'll go ahead and select as many or as few, and we're seeing breaking apart into 2 add-ins, we're seeing place value. Okay, now we have break apart in more than 2. Very nice. Okay, so everybody that I'm noticing does break apart into 2 add-ins. A fourth of the audience is breaking apart into more than 2. And then we have about 2/3 of the audience, well, 6/10 of the audience breaking apart into place value. Very nice. Okay. So we're going to move on to the next one. One more poll here. And when you look at this, what tools do you use in your classroom? Because I feel like as educators, we always learn from each other. And I'm always very interested to see what other people use as far as math in helping children understand computational thinking or just math in general. Okay, I'm seeing a lot of 5 and 10 frames, some Unifix cubes, digit cards, dominoes. Nice. Okay, we'll wait just a few seconds more to make sure everybody's had a chance to respond. Instead of bland 100 grids, we're going to make that blank 100 grids. I love that. Okay, so it looks like the most are Unifix cubes, 5 and 10 frames, digit cards, and dominoes. Okay, wonderful. Thank you. Now, a final note before I leave the math portion of decomposition is to make sure, I guess I need to, hold on, Sarah, my handy-dandy assistant, is helping me out here, is to read the article, The 13 Rules That Expire. This was published in 2014 in the Teaching Children Mathematics Journal by the National Council of Teachers of Mathematics. The rules are well-intentioned, but they prohibit the long-term success of children as mathematicians, and it's a really quick read, but well worth your time. So at this point, I'm going to turn it over to Lisa.
Thanks, and I love how you were talking about breaking down numbers in different ways and how to decompose them, because number sense and fluency are so important. And as elementary classroom teachers, we have that advantage of being able to integrate concepts more. I know that in my classroom, we start almost every math class with number of the day, and students are asked to represent a given number or a solution to a problem in multiple ways. And then when students are able to decompose that number in different parts, they're showing a deeper understanding. And even today, one of my students represented 135% by first breaking it down with base 10 blocks, then wrote each part out using decimals, and then brought it all back together as 1 and 35/100. So it's just kind of cool to see that, as you just mentioned. That being said, we're able to use the strategy of decomposition across curriculum. In language arts, we tend to work on longer range projects. One way we are able to utilize decomposition is to just break down a large task that can be really intimidating to students, or a longer time frame, into smaller, more manageable chunks to ensure we're getting everything accomplished and we're getting it done in the most efficient way. We can also decompose stories into smaller chunks, whether it's just looking at beginning, middle, and end, or taking a deeper dive into narrative structure to include exposition, rising action, climax, falling action, resolution. We're going even deeper, just picking apart a story to look at character and character change, the setting, the conflict. Breaking down informational text can also be overwhelming to students, especially texts that are more dense or vocabulary rich. So you could discuss strategies for decomposing these types of texts into more manageable chunks to gain a deeper understanding. This could be by cluing into text features, such as headings and subheadings, and how do they help you. Looking at visual supports, such as photographs and diagrams, and then how they fit into the bigger picture, and how everything works together so that you can help monitor your comprehension and support your reading. Another way to utilize decomposition in language arts is through word study. Whether your students are working on beginning blends, or working on endings, roots, affixes, suffixes, by decomposing words into smaller chunks, you're supporting students learning spelling patterns as well as the meaning and usage of different words, and then you start to build connections and families between words. So really, there's lots of different ways to decompose within language arts.
So let's focus in on computer science. Decomposition in computer science can be started at an early age with a program like Scratch or Scratch Junior. Teachers may ask students, how can we make this kitten in Scratch Junior dance across the stage? And then guide students in creating an algorithm with smaller steps to accomplish the task. But it doesn't always have to be with a screen or block coding. It can start with unplugged activities such as, how can we tell a partner how to draw an image we see and that they don't? How can I give instructions to a partner to walk across the room in a certain path? Decomposition also can be used in many different circumstances, such as drawing out the steps that it takes for a seed to become a plant in science, or through the use of graphic organizers in all subjects, which can visually show young students how to break apart large amounts of information into manageable pieces.
So we just provided a whole lot of information. If you just take a moment and in the audience chat, think about a takeaway. What's something that you want to dig into a little bit more? What's something you might want to use and take back to your school? Just take a moment and put that in the chat. So measuring growth in computational thinking. Okay, we're going to keep going, but we'll keep talking about takeaways throughout.
Thank you, Lisa. Having an opportunity to decompose a problem into smaller pieces also allows students time to identify patterns. Our next segment of CT is pattern recognition. In this step, students analyze and look for a repeating sequence. So 10 years ago, I took a course through the Mathematics Education Collaborative, and this is with Ruth Parker and Patty Loughran. It was called Patterns, the Foundations for Algebraic Thinking. The math tool that we utilized repeatedly, I've drawn on this slide, and it was simply called a what I see table. The purpose was to notice and physically name or sketch out what you were seeing as you thought about your math problem. So the teachers were acting as students, and we used the what I see table to quickly identify patterns. And this was also a lesson in metacognition for me as well, because as we identified patterns that we saw, we wrote down how we came to find these patterns. Were we using skip counting, multiplication? Did we have to break numbers apart? And then we were simply writing what we saw just as the table indicated, what I see. Next, we explained why what we saw was important, and we began to think in terms of next step as we were moving towards a different solution. This simple tool was an eye-opener and totally changed how I approach problem solving. It also made me a very firm believer in visual models when working through a problem.
In language arts, when I approach pattern recognition, think about trends and try to frame patterns a little bit differently, particularly in the upper elementary, thinking about patterns in multiple ways. This can take the form of looking at patterns that you can see over a genre, different types of text on a particular topic, or it's different text from a certain author. So what commonalities do you see across the different texts? What makes them similar? What makes them different? And another way to think about patterns is through text structure. Text structure is such a powerful tool to aid in comprehension. When students are able to identify the structure or structures that an author uses in a text, they're then able to more easily organize that information in their head as they read. And so if a text utilizes the cause-effect structure, then students can have that pattern ready in their head or even in a graphic organizer to note key points such as what happened and then what was the result, or vice versa. Pattern recognition also lends itself really well to word study. So going back to what we talked about previously, thinking about trends in patterns when you're spelling things and how words are used. I'm going to turn it over to computer science.
So in computer science, there's a lot of places where patterns can be observed. For example, between different pieces of software to interpret meaning, such as the triangle in usually K2 software usually represents play, or a green circle often means go. Also, the patterns of color in Scratch typically represent different functions. And the same colors can be seen in younger tools such as Scratch Junior. In block coding, where students can see an action by a character, it's repeated many times. They are able to recognize this repetition and construct a need for a loop block encoding. And patterns also can be observed in weather in science. Through computer science, students can create meaning of their world that they live in with the patterns, and then can apply those same principles in coding.
And funny thing, so when we were preparing for this webinar, we were talking about just all the different resources we were using, and then today I had a colleague to email me a blurb regarding graphic novels. So I told Lisa, I said, Lisa, you're not going to believe this, but they have graphic novels that have a math storyline. And it's not really for K1 and 2, but it started with multiplication and division and talking about exponents and powers of 10. And I thought, and the premise of the novels was hilarious. And I really want to get my hands on one of those to read it. But it made me think of Lisa and doing English language arts and just everything that we're talking about tonight and how it all tied together.
That's awesome. I can't wait to actually find out the title for that.
Oh, me too.
Or some of the different titles. Yeah. So if we could just take a moment again and see what takeaways you're having from this, what questions you might have, things that you want to dig into deeper, and just put that in the audience chat.
And as everybody's typing, thank you so much for your questions so far, because that helps us know a direction for tonight's conversation. In case you have something that we have not addressed so far, we would love to know any questions that you have about computational thinking.
We'll just go ahead and pause there for now. Take some time. If you have something that you have a question about throughout or another takeaway, feel free to add it throughout. Tim, I see you say, what projects do you see as a good capstone project to assess that students are learning computational thinking standards or skills?
That is a very good question. Let me think.
Is there a particular grade level? Yeah, let me think on that too. Sorry. Nancy?
I love that. I mean, I would be very interested to know if Tim does have a specific grade level in mind, or and also how many different areas do you want to incorporate? Are you thinking about making it a cross-curricular capstone project?
Yeah, the code.org is a fantastic resource. Has a whole bunch of different things, whether you want to do unplugged or plugged lessons. And they do incorporate math and reading. So, and it really depends on the grade level.
True. Hey, Tim, you're unmuted right now, so if you want to elaborate a little bit for everybody, we would love to hear.
Okay. Thank you. One of the things we're doing, we're piloting a computer science integration plan in our elementary school this year. And of course, one of the big components I feel is you have to assess as you go along. to understand if you're doing a good job, to understand if the kids are picking up the concepts, and then kind of tweak your program as you go. And I think vocabulary assessments are good for that, to see if they're starting to understand the vocabulary, but also to do a project that shows they're really understanding the concepts, too, of computational thinking / computer science / coding. And just wondering if people had ideas along those lines as to what would be a good way to demonstrate that the kids are acquiring the skills. And, you know, each year, obviously, sequentially, you want to make sure that they're, just like any other content area, that they're growing.
I like that you mentioned the vocabulary. We're kind of in a similar spot in our district where our state just developed computer science standards starting in kindergarten, and we're kind of in the same place. Like, how do we encourage that vocabulary starting in kindergarten and growing up? So we're kind of in the same place that y'all are. I really like the CS First. They're actually the coding club sets. But to me, those are great for creating a project for the kids to be able to demonstrate what they've learned during the whole course.
Yeah, we use CS First. I've just started that this year, like that also. We're going to do Kahoot quizzes, and I'm trying to figure out sequentially how we're going to build from K to 5 with the vocabulary, just like you would in language arts, just like you would in math, kind of that sequential order and scaffolding the concepts. So I guess everybody's kind of in that same boat.
Yeah, but I do think
I think it is something. Oh, sorry.
No, go ahead.
No, it's just thing. I think that there are, there's so many different schools that are feeling a little bit overwhelmed with, integrating in holistically, because it's kind of like one additional thing. But finding ways to kind of like build that vocabulary. I know one way that we've been doing at my classroom is we've kind of integrated the robotics and programming and looked at ways that, we're building Mars rovers because we're learning about astronomy. We're going to other planets, and then we're writing about that. And it's really through the journaling, like how are you using decomposition? How have you used algorithmic design? How have you found patterns to solve your problems? And it's all through that journaling process that they're showing their thinking and how they're building upon it. And so it isn't dependent on what their previous skills necessarily. I'm looking for growth from the beginning of the year, student by student. And you can do that with any sort of project that fits your curriculum.
Hey, Tim, one thing that we also used a couple of years back with some elementary kids was App Maker, and I think this is the right one, I'm not for sure, but it was through code.org, and the kids were very interested in making an app that would also make an impact on the community. And so we had a special guest speaker to come in to kind of help us go through some design thinking, and as a group, the kids were building out what they wanted the app to do, how they wanted to make a difference in their community, and then they also had to figure out how they would know if they were successful or not. So we built it in theory, but I did have some kids that on a different project, they were looking more at choose your own adventure type activities. So theirs was totally story writing. But if I find the right program, I will connect somehow and let you know what that is, because I'm looking at App Maker, but it doesn't quite look like what we used before. But if that helps at all, that's one use of developing a project, and that one included communication, mathematical thinking. Well, it just everything with computational thinking, because they had to decompose what the issue was. Ooh, maybe. Okay, so Sarah's pulling up MIT App Inventor. It could be. Yeah, so take a look at some of those. App Builder, code.org, and MIT App Inventor. Alrighty.
I agree, Tim. I just saw where you said unplugged lessons tend to be overlooked. I couldn't agree more. And a lot of our 4th and 5th grade teachers overlook them very quickly, and I think that they're so valuable. We try to do them as much as we can.
I think Michelle is going to unmute you, Tim. There you go.
Thanks. Yeah, full disclosure, I'm a Code.org facilitator, and so I'm still learning. There's a lot to learn still, but I've enjoyed some of their strategies. And I see we have one friend from Virginia, and I got to be part of the Virginia Coaching Academy this summer. Virginia's rolling out the elementary standards. I believe they're the first state in the country to fully integrate elementary computer science standards into their curriculum. And I really like what Virginia's doing in that regard, just putting it into every curriculum area. So they're doing a very good job from what I got to see this summer.
Awesome.
I'd love to hear, Kelly, about your ideas for K-5 vocab.
Can you hear me?
Yes.
Oh, awesome. So I'm assigned to a school in the Bronx as a coach. I'm on a contract there through a grant, and this is our second year working with how do we integrate computational thinking into the curriculum, and we've kind of we think of it as a universal language for problem solving across the curriculum. So it's almost like an umbrella that when elementary teachers are teaching math or they're teaching science or ELA, they can always refer to that language in decomposing any task. So the first year was a growing year, but the way we were able to really onboard the teachers and the students was through what we call a monthly task in math and ELA. So before I arrived, they were trying to get kids to do more collaborative work. So they're up to what I call them events, 3 events per month, where every child in the school works with a partner to solve a problem in math twice a month, and then in ELA once a month. So that time is dedicated to really introducing the language of computational thinking, of decomposition and finding patterns, and using actually abstraction. So we've been able to build the faculty and students over the course of these events that happen each month, where they're feeling extremely comfortable this year with using the vocab in their everyday lessons, and get kids to think about their thinking. So it's come just using this event, I call it the event per month, and having the teachers practice using the language in problem solving with the kids, and asking the kids questions during the share out part of this event. The entire school is really developing their knowledge about thinking about their thinking for solving problems.
Nice.
And it's pretty amazing because it's really inquiry focused. So the teacher reads the problem, reminds the students to don't forget to think about the computational thinking skills that they can use to solve the problem, and then the teacher stops speaking and the kids work collaboratively and talk about different approaches to solving the problem, and they actually solve the problem as the teacher watches. And then she calls on a couple of pairs to share out their thinking, and then she will say, okay, during this process, what computational thinking skills did you think you used? And there's no right answer. I mean, one kid might justify why they might have used a lot of decomposition, another might have said, I use abstraction. And we've had 4th grade students talk very correctly about how to use abstraction in solving an ELA problem. So it's kind of mind-boggling, but it's working.
Oh, that is awesome. And I see Tim is asking, he said, would you be willing to share a model of that plan? And I think all of us are like, yes, us too, us too. So if you have a link to something along those lines, we would love you to share that out.
Yeah, I have. My big issue right now is I'm trying to figure out how to assess growth in thinking, in computational thinking. So we introduced this to the kindergartners this year who just joined the school, and they too participate in these tasks. where do I get my baseline in the beginning of the year, and then how do I measure it at the end of the year? So we're kind of tinkering with videotaping what we call the share-outs and trying to code them. So we're going to try to, as a community, try to see if there's a way to code a level of thinking for a particular concept.
I love that.
That's
That
fantastic.
is real cool.
I remember seeing some of your examples at CSTA this past year, and I was just blown away by some of the thinking that the students were sharing.
Yeah, it's pretty neat, pretty incredible. And now it's year 2, so things are a lot. We've grown a lot in the second year.
Right. Awesome. Yeah, we'd love to see some of your resources, and then the assessment part is always hard, right? Like, how do you, especially when you're assessing like a thinking level, like, so I think it's definitely something that's going to be a work in progress for all of us as we dig into this deeper.
Nice.
Thanks so much.
Yes, thank you so much. Okay, we're going to keep moving. So our next area, after students have an opportunity to think about how to decompose a problem and draw a visual to look for patterns, they now enter into the third phase of CT, known as abstraction. So when we think about this, helping students sift through and remove extraneous information. We want them to reveal essential concepts and understandings because those are valuable tools. In math, when students realize the concept of hierarchical inclusion, that all numbers preceding a number can be included in the value of the number before, or that specific number, this is valuable in the decomposition process. So place value is also valuable for abstraction because students understand that it helps them to understand problem solving across the board. They play with values of odd and even numbers, and they realize the patterns help them to develop number sense. Hold on. Okay, so this is one thing my students always loved when they figured out patterns and they were able to draw a conclusion, which they then put to a test. For example, every year in 3rd or 4th grade, students played around with numbers, and someone finally made the statement, hey, an even number plus an even number will equal an even number. Or they came up with, did you know that an odd number plus an odd number also equals an even number? So when we talk about how this works, we use visual models, or we write out our thinking to confirm our thought process. This writing helps us think about our thinking, and it also serves to help us defend our position. Proving our thinking might look something like the example of 11 plus 15. Each number is broken apart into a number plus 1. In this case, you guys can see 10 plus 1 and 14 plus 1. So we have 10 and 14, both evens. And to this, we add the 1 plus 1, which makes, another even. And then you add 2 odd numbers together. What you're really doing is you're adding an even number. In this case, well, I already said 10. But what it breaks down to is instead of 2 odd numbers, essentially, you're adding an even plus an even plus an even number. So the next step is, can I write a rule for this? And that's where I think when you're talking about assessing kids as part of the computational thinking, that would be one area. If they can write a rule for that, and that would just let them know, oh, okay, yes, I'm thinking through this and I'm thinking clearly.
In language arts, in terms of abstraction, we often discuss how to effectively communicate a message, whether this is through oral communication, written communication, or we're analyzing decisions that authors make. So what's key to get your message across? Think about when we ask students to summarize or tell the main idea of something. Too often, they'll retell the entire story and provide too many details. By using abstraction, we can focus on what's essential for sharing our message, and then think about what can be left out. For example, if students are writing about the relative size of planets in our solar system, they do not need to include information about distances between planets, the temperature of each planet, atmosphere of each planet, but they could include information such as the diameter, comparisons using ratios or proportions. And you can do this while you're editing a piece of writing, during the planning stages, or through discussion. So it's just another lens to look at how do we effectively communicate our message, what do you need, and what can you leave out?
So in computer science, for abstraction, young children can often develop the concept of abstraction by using sorting activities and deciding what attributes will be used to categorize like items. We can also ask students to think about what is not necessary in code, what can be left out of the code to help with meaning and for clarity. One of my favorite activities from Code.org is to give students code and then ask them to debug it or to simplify the code.
So take another moment, takeaways, other questions you have, things that have sparked you to think deeper. You can go and hop in that chat box again.
Mm-hmm.
Yeah, Tim, debugging is definitely a great strategy. It's one that we go to a lot. How can we think about something a different way? How can we pick it apart and fix an error or a mistake?
And also that errors are just opportunities for growing and learning.
Right. And one thing I told
Absolutely.
Lisa.
At Pi Academy, they
yeah, go ahead.
At Pi Academy, they talk about failure as your first attempt in learning, and I love that. I start the year with your first attempt in learning. It's okay. Keep going.
Yes, that's important. And I told Lisa earlier, I said, I'm going to go ahead and pop in this YouTube address for Josh Darnett, because when she was talking about the process of telling kids how to do, like a to-do paper, and so you're writing and you're trying to explain how to do something step by step, then this video came up, and it was a dad whose name is Josh, and he is trying to get his children to write and tell him how to make a peanut butter sandwich. So it is hysterical because the daughter continually comes back and she's refining, but the son at one point, he just looks at him, and you can just tell it's just utter disgust. He does not want to do it, and but it's very nice as far as the kids learning precision of language. And how computers also think in this manner. They're only going to do exactly what you tell them to do and nothing more. And I thought what he was showing was just a perfect run through of how to do something step by step.
Absolutely, Paige, about the perseverance.
Yes. Thank you. Okay, so the final phase of computational thinking is algorithmic design, the step-by-step directions on how to perform a task or form a solution. When students are able to look at the parts of a problem and then have the time to ponder the problem, to draw visuals, to use manipulatives, they can also think through their work in order to find patterns. At this point, essential enduring understandings are abstracted, which lead them to the final step of being able to put a plan in place, or in mathematical terms, to develop an algorithm. Let's put our computational thinking to the test on the problem above. So think of yourself as your students. And if I'm a student seeing this problem in a number talk and combining what I know about CT, my first thought is to decompose. What am I being asked to do, and what strategies do I know? Revealing patterns is my next step in CT. I can do this by making a visual model, using a what I see table. I can use the manipulatives, or I can begin drawing it out on paper in a different way. Next, I think about what is important to know. Hierarchical inclusion is very important. In this particular problem, I began thinking of what numbers can be used to make up each number. I can picture the magnitude of the number, and I can visualize the numbers and the sum on the number line. I consider the place value of each digit, and then finally I think about past discussions regarding odd and even numbers. So we're getting ready to conduct a quick response as you would in a number talk. So put yourself in your student's shoes for a moment. Find the student icon at the top of your screen, and I need you to respond. So here's your question. Will you please raise your hand if you think the sum will be odd? Also, I have one more part. I want you to defend your answer in the chat box. So raise your hand if you think the sum will be odd, and defend your answer, please. We're going to take just a moment. And thank you for being kids for just a moment. Okay, all right. So we're going to move on, and we're going to clear out our responses here. I'll put it back to raised hand. Here's your second question. Will you please raise your hand if you think the sum will be even? And I need you to defend your answer. Oh, Diane, I like thinking of the many different ways to solve the problem. Yes, yes. That's always a very good strategy. Tim, I love it. Yes, evaluating is a CT skill. Thank you. Okay, one more question. Remember to think as your students would, and now respond in the chat window to this question. Will the sum be greater or less than 100? Make sure you defend your answer. Okay, we're going to take just a couple of more seconds. So through participating in this online number talk, you have just completed a sample of how we could use CT in the classroom during a number talk, because we decomposed the numbers, we looked for patterns, we abstracted by thinking of the properties of addition that we can use to solve, and then we're working through a final solution. And now we're going to turn it over to Lisa. Oh, I like the estimating by rounding up. Yes, very nice. Paige, thank you.
Language arts. Oh, yeah, go ahead.
No, that was, I was just noticing what they were.
Yes, we had lots of good thinking over on the side. And, you know, people reducing computational thinking to a shorter list and just not really thinking of broader it's hard, because there's all sorts of different skills that go into being a computational thinker and into programming, that when we try to isolate all these just individual skills, we're not really getting the bigger picture. So in language arts, algorithmic design can take the form of creation or directions to complete a task, whether that's how to build a peanut butter and jelly sandwich like Nancy talked about, or how to draw a certain image, create a letter, or how to complete tasks within a classroom. Using that precise language is really key. This also can lead to conversations about what makes a story, what are necessary elements to build a narrative. Think about the exposition, rising action, climax. What's that formula or algorithm for a good story, or is there one? What happens when our writing becomes too formulaic? Can we start with a basic algorithm for a story, and then how do we deviate from there? How do we iterate and make it our own? This also can lead into really good discussions, thinking about AI and algorithms writing news stories. And there's even some articles out there about, can an algorithm write a better news story than a human reporter, and then how do you know? So it can lead to some deeper conversations as well.
So students in elementary years can start to develop a sense of algorithmic design by noticing that most programs have a certain syntax that others understand when they're trying to follow the program, such as direction, repeats, and if-then statements. Flowcharts can be used to organize the events in a sequence. For example, students might use flowcharts to explain certain steps in the process of making a peanut butter and jelly sandwich, like Lisa's example, and they will eventually start to see the basic flow of coding. Most start with an event, have a sequence of actions, and then have an ending. This knowledge can then be translated to harder coding concepts such as if-then statements and variables. One example that I love to do with students is to lead students through algorithmic design through an unplugged activity of Happy Maps from code.org, where students use arrows to tell the character of the flurb which way to go and travel on the grid. And then they use those arrows to be able to tell somebody else how to travel the flurb in order to get to the apple. So let's kind of take this into a broader sense and look at it into one activity. Currently, one of my favorite CS tools for kindergarten through second grade is Kibo. I think this is a great tool for K2 in particular because of its easy to manipulate wooden blocks and also the screen-free interface. Students connect wooden blocks which have dowels and a hole to create a sequence of code. Each block has a barcode which can be scanned by Kibo to program the robot. I love that this robot encourages young students to play while working with computer science concepts. So to give you an example of teachers, how they've used Kibo to teach computer science, let me tell you about one recent activity. One of our librarians at one of our elementary schools has a semester-long makerspace. She asked for dads and mentors in the community to come in and lead the stations of their choice. Typically, the mentors are parents who have backgrounds in coding or computer science and often include information about their careers. So one of the centers we planned around Kibo and computer science, it was bowling with Kibo. And about 4 students and the mentor were tasked with programming Kibo to bowl. The plastic bowling pins were set up at the end of the long sheet of paper. A starting point was placed right in front of the pins, so the students could knock over the pins with a simple algorithm of start, forward, and end block. This allowed students to think of the algorithm as a basic, decomposed manner. And then the next step was to challenge them to continue thinking about the algorithm in order for it to be a little more complex. So they had to start further away from the bowling pins, and then they had to use several forwards in order for the Kibo to travel the distance down the paper. But we intentionally just left out one forward block in the kit. The groups had to decide how to program Kibo where they were several forwards in a row. A pattern developed, and then they saw that they would need a forward, 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 and so on until they reached the pins. They quickly realized that they would have to scan the forward block 7 times in order for it to get to the end. They later discovered that a repeat block in the kit and realized that they could use this block instead of the multiple forward blocks. Then the third challenge was to start at a right turn and then continue down the center of the paper in order to knock down the pins. The students coded originally left, which is kind of a common mistake for young kiddos because they have a hard time thinking about the perspective of the Kibo. The mentor was able to talk to the students about bugs and debugging at that time. A simple engineering cycle developed without the students being explicitly taught these steps. They looked at the big picture, that they wanted to knock down the pins, and break down it into manageable pieces by physically building the algorithm with those code blocks. Then they made it a little bit more efficient because they decided what they really needed to do was to move forward several times. At the end, they tested their theory, fixed when needed, and then ran it again. So the parent or the dad that was with them talked to them about decomposing the algorithm until they knew that there was an issue, and then they fixed it. And the students were, again, able to go through the thinking process of looking at a big picture, break it down, ask what do we really need to do, and then they tested the algorithm. So I love this activity because it kind of shows all of the 4 parts that we've been talking about. So the students were looking at that task sequentially. They used decomposition in order to fix the bug in the program. They were able to see that pattern that was developing. They were able to determine that the repeating forwards weren't needed, and then use that repeat block in order to make the program more efficient. And then, at the very end, they were able to develop an algorithmic design and apply it to some new programs. So, for this poll, I'd love for you to tell us what are some other extensions that you think we can try with this activity. Oh, absolutely. I think loops would be a great extension for this activity in determining how many times that you could go forward. Oh, I love that, Kelly. Yeah, it's programming the keyboard to go to different letters of the alphabet on the grid map. Spell a word and find numbers. That's an awesome activity. I love that. All right, that's awesome. So I've got a quote just to kind of wrap it up. So the creator of Kibo, Marina Bear, she was quoted as saying, "Coding can become a playground, an environment to be creative, to express ourselves, to explore alone and with others, to learn new skills, and to problem solve. All of this while having fun." I think that just kind of sums up what computational thinking is all about in computer science. That playground in order to be expressive and to be able to create.
And this is an incredibly wordy slide, which we're not reading, but I just wanted you to take a look at the standards for mathematical practice. And as you glance through, you can just see that every part of computational thinking is woven throughout mathematical practice, beginning with number talks at the beginning of a lesson, doing our turn-in talk time in the class, making visual representations during our small groups, and also providing opportunities for our students to have discussions using mathematical discourse, and then also just making sure that you have a final debrief at the end of each one of your classes.
Then thinking about English language arts, and I know, again, this is a lot to look at, but since we all have different standards and different states, then thinking about guiding visions. This is from NCTE. So overall, though, thinking about how can we incorporate things in different ways, there's not one way. And looking at innovative and creative ways to do that, that's going to include critical thinking skills and computational thinking. And I really love that when we can bring in different avenues, so whether we're coding a story in programming our robots to act out something like the characters, or if we are just journaling about our experiences, we could interweave those thinking skills, whether you were debugging, you were decomposing, you used an algorithm throughout the day, and it's not just in this time where we do computer science activities.
And of course, we can't talk about CS without the ISTE standards for students. And this is the computational thinker strand in here. But it's just so happens that I got my ISTE magazine in the mail today, and there was a booklet included on computational thinking meets student standards. Has some great practical ways of implementing that. So if you are an ISTE member, check that out in your mailbox.
All right, so here's a listing of our resources. We're going to have to go pretty speedily, but we want to thank you for joining our webinar on viewing elementary CT from different perspectives. This webinar was meant to provide awareness as to what computational thinking is, how it can be easily integrated into a variety of curricular areas, and to provide you with resources that you can use in your class tomorrow. Okay. We're going to have a survey at the very end, so if you can hold on for about 30 more seconds. And if you enjoyed this webinar and are looking for more resources for elementary, middle, and or high school, please register with CS for All Teachers. It's csforallteachers.org. The account is free, and our community of ambassadors are all educators. All the information provided tonight and through our community group webinars, blogs, multimedia presentations, Twitter chats, they're all derived from being tested in the classroom first. So we invite you to make an account and join us, and you can access CS for All Teachers at any time. The best part is you get to do it in your PJs most of the time. So at this time, I'm going to turn it over to Michelle Perry.
Thank you, Nancy, Sarah, and Lisa. This has been a wonderful webinar. Thank you all for attending. Feel free to follow us on Twitter at CS for All Teachers, minus the vowels in the teachers part, or come visit us on our website. And we'll be posting new events each month. Check out our events calendar. Thanks again. Have a good evening.
Good night, everyone. Thank you for coming, and thank you for contributing. Aw, Paige, Kelly, Tim, thank you so much. That means a lot. Thank you, Diane.